So in this lecture, I want to talk about several several powerful reactions that involve transition metals. And we're going to start with the Vocker oxidation. So the Vocker oxidation allows for the transformation of an alkene into an aldehyde. So in the Vocker oxidation, what you do is use, we have some alkene source, and we're going to add that to water. And then over the arrow, we're going to have palladium chloride. So I don't need a parenthesis around there. Palladium chloride as a catalyst. And I have copper chloride as a catalyst. Both of these are the dichloride form. And then we're going to have oxygen. Let me just check to make sure. Yep, I've got that right. So then we're going to have oxygen also over the arrow. Okay, so the outcome of this is we're going to convert that alkene into an aldehyde. So this is the Vocker oxidation process. It's kind of a complicated mechanism, but pretty cool one. So the first thing that happens is let's consider the palladium catalyst as our starting material. And there's a nice way to draw this as a circular catalytic cycle, but I want to walk us through kind of a day in the life of some of these atoms before we worry about trying to turn things over. So the first thing is the palladium catalyst is going to form a pi complex with the alkene that's going to do the reaction. So the pi complex is going to look like this. Now, the reason why I like to talk about this reaction is that this reaction points out the fact that if a pi complex is being formed, and I've said let's consider a pi complex as a Lewis-base interaction. If that's true, then it turns out that something else has to be a Lewis acid, and that's the metal center. The metal center is going to be a Lewis acid, and when we have Lewis acids, they activate pi systems to make them more electrophilic by pulling away electrons. So if we're going to be more electrophilic at the pi system, we can start to react with some nucleophiles like water. So when we do this, we actually add to the terminus end of our alkene and then push the internal side of our alkene onto the palladium to form an actual monovalent interaction. And along the way, sort of ligands are sort of coming on and going off. So I don't worry too much about being meticulous in my electron count. I want to capture the important details. Now it's at this stage, there's some debate as to what happens, but in terms of ligand substitution. But the key event we want to make note of is that after we form this sort of palladium alcohol species, is we can undergo a beta hydride elimination. So a beta elimination to extract a hydrogen. Okay, so that's going to be kind of this retro 2 plus 2e arrows, and the palladium is going to accept the hydrogen. Now, when the water attacked, I forgot an arrow. I'm sorry. Let me just back up a second. I jumped the gun. Okay, because I made the classic mistake of assuming that we've gotten rid of this H plus, and we didn't. What happens is the H plus gets lost in a deprotonation event, and simultaneously a chlorine atom is lost from the palladium complex. That's going to give rise to an HCl molecule. So we do a net HCl elimination to give us an intermediate that can undergo the beta hydride elimination. Sorry, I screwed that step up. Now we're at an OH. Now we're at an R group, and we've only got one chlorine atom attached. That's important for later. So now we're going to do a beta hydride elimination where the palladium picks off the hydrogen and eliminates an alkene to give us this palladium complex. Now, perhaps adducted by way of a pi complex that dissociates so this may have been a pi complex that dissociates, but let's go ahead and just let it fall off, drop off the metal center. What I want you to recognize about this structure is that after we undergo the beta hydride elimination, we form an enol. And enols exist in a favorable equilibrium towards, or an unfavorable in their regard, an equilibrium that favors formation of a KetoForm, which is going to be our desired product. So the KetoForm. Now, what's interesting about this product is there's a few mechanisms for it. It's a net I'm just going to call it what it is. If you have palladium HCl, so palladium with an H on one side and a chloride on the other side, this will spontaneously do a sort of, it's kind of a more of an elimination-like reductive elimination, but it's a reductive elimination nonetheless. We can actually do a reductive elimination to make HCl plus palladium, and in this case, 0. Now, what we'll see for the rest of the lecture is typically this is not, this is our catalyst, this palladium 0 center. But for the Vocker oxidation, this is not catalytically active. Now, if you notice, we've actually generated our product up to this point. We haven't regenerated our catalyst. Our catalyst was a palladium 2 center, palladium dichloride. So it turns out that when you have palladium 0, okay, that can react with a copper species. So this copper species will regenerate palladium 2 plus, which you can then let a couple of chlorine ligands kind of come on to. I shouldn't write that as, I should write 2Cl minus plus 2Cl minus gives us palladium dichloride. Okay, now this Cu, if you recall, we added copper chloride. So what we're going to do is we're going to take copper chloride plus HCl plus O2, and these things combined will make, if we have 2 of these, we will actually get 2 copper chlorides, but we go from copper 2 plus to copper 1 plus. And this isn't a great oxidation state for the copper, and so this is going to react readily with something so that it can be let's see, do I have that right? I feel like, gosh, that's not making sense. Okay, I think what happens, this is Willoughby just kind of going off on his own. I think the palladium 0 interacts with the copper chloride to make palladium dichloride plus copper 1 chloride. Now, copper 1, just ignoring Wikipedia at this point, just going off on my own. Copper 1 is not a stable oxidation state. And so copper 1 chloride, which is copper 1, is not a stable oxidation state. I've handled it. It turns blue pretty quickly as it reacts with O2 to form a copper 2 plus species. So we probably need some HCl in there to make copper 2 chloride plus H2O. All right, I'm going to put X and Y. We need some amount of oxygen and HCl, but that's going to get us from a copper 1 chloride to a copper 2 chloride. It's a very easy reaction to pull off. So it's actually palladium 2 that induces the Vocker oxidation, which were the earlier steps. And then what we use the copper chloride, which is dirt cheap, and the oxygen for is to turn the palladium back into palladium 2, which we can use. Okay. Now let's get to some more straightforward transformations and some more powerful transformations. These fall in the class of reactions called palladium-catalyzed cross-coupling. So there's sort of there's a series of these we're going to be talking about. I'm just going to count them. I've got them counted in my head. So we're going to talk about 4 of these, and these are super powerful reactions, and several people have shared Nobel Prizes for them. We'll start with the Heck reaction. The Heck reaction makes alkenes. If we're going to make alkenes, we're going to rely on a beta hydride elimination. But all these reactions kind of start the same. So what we do is we take an aryl halide and we kind of mash it with something else. And in this case, the reactant is a terminal alkene. So sp2 halide, I guess it's a CsP2 halide, and we're going to merge them to get couples with an alkene. And this makes an alkene. Okay, so the outcome of this reaction is, if we have palladium 0 from some source, we're going to actually form an alkene and HX. I had to flip my alkene over. Sorry about that. Okay. So what we did in cross-coupling reactions, we take two molecules that are completely separate and otherwise unreacted, and we just add a little bit of pixie dust of a catalyst and cause those two things to find each other and react. These are things that are not predisposed to react in the absence of the catalyst. Having that palladium catalyst present means that we can do this reaction. The mechanism for these reactions tends to begin, first of all, with oxidative addition. Okay, so the first step is oxidative addition, where we take our haloarine, our aryl halide, our benzene ring attached to a halogen, and we react it with palladium 0. Put the 0 in parentheses. Now, this is going to undergo an oxidative addition event where the palladium squeezes in between the carbon-halogen bond. When we do that, we're now in the +2 oxidation state on palladium. Okay, well, what we can do from here is we can kind of do like what we did with the Vocker oxidation and engage our alkene. And these alkenes could be anything. I don't mean to just pick on, I don't mean to just pick on these two species. So this alkene could be anything. And so we're going to let the palladium, just like in the Vocker oxidation, I'm just going to label that as phenyl next to palladium. That's not wise. That's going to be confusing. Is we're going to form a pi complex to the alkene. Now, from a pi complex, and that's a ligand association reaction, now we're going to do a migratory insertion reaction. So the migratory insertion kind of looks like a 2+2 type of reaction. Now, what are we actually doing migratory insertion with? We're going to go here, and then we're going to go here. So we're actually going to make a carbon-carbon bond. Okay, so we make a carbon-carbon bond. I'm going to keep my alkene the same. Now, what happens is the palladium goes to the more substituted side of our alkene. And the thing we're coupling with goes to the less substituted side of the alkene. Now, what the palladium is going to do is it's going to do the opposite of a migratory insertion, and that's a beta elimination. But instead of grabbing the aryl ring, it's going to grab the hydrogen atom. So we do migratory insertion to beta elimination. And with beta elimination, this is hydride elimination, by the way. With beta elimination, we're going to form an alkene. Plus palladium, and palladium was still attached to X this entire time. Palladium attached to X and H+. What we have here is our coupled product. And it turns out that in many cases, palladium in the +2 oxidation state, if you kind of remove oxygen, you can get back your palladium 0 complex, which is your starting complex. Now, how do we do that redox process? In many cases, it's not actually clear. It just seems to work if you have some sort of base present. Here, it's not so hard to see what happens with the base. The base is going to grab the hydrogen, push electrons into the palladium, push electrons off of the X group. And if you actually do the electron count on this, you're going to see that we end up with a palladium 0. So we usually have some sort of base present in a lot of these cross-coupling reactions to help us turn the catalyst over. It's not always super clear why it works the way it does. Although in this case, it's kind of helpful because we perform that palladium hydride with a halogen attached. So we can just eliminate HX from the molecule, from the reaction, and this sort of works. Okay, so another example of a cross-coupling reaction, if you notice we make an alkene here. So what's kind of critical about the Heck reaction is you form an alkene product, right? We have to do oxidative addition, pi complex, migratory insertion, reductive elimination, and then turn your catalyst over. So because you have migratory insertion, reductive elimination, you always form an alkene product. Sometimes we want to just couple and just make a bond, right? I mean, alkenes are cool, sure, but we could have an alkene as a starting material and just couple it to an aromatic system and avoid this whole, and maybe there's a way to stitch it together more directly without requiring an alkene product. It could be an option, but not a requirement. That's where we're going to look at some other types of cross-coupling reactions. So I'm going to move not in chronologically order at all and go right into the Stille cross-coupling. So the Stille cross-coupling involves taking an sp2 hybridized organohalide, and that could always be like an X group attached to a halide, or excuse me, an X group, which is our halide attached to either an alkene or a benzene ring. And we're going to mix that with, and let's go ahead and make our tin a tributyl. We're going to mix that with an organostannane, a tin reagent. Stannane is kind of, if you remember, SN is tin. So an organotin reagent, again, in the presence of palladium 0, that's going to couple this R group to either our aryl or our alkene. So the alkene could be a product, but it's not a requirement. It's not like a fundamental piece of the puzzle. Now, this reaction I like as the next cross-coupling reaction to show, because it shows a very simple sequence of events that we're going to see over and over again in different settings. Okay, the first step using either of these halides is reacting the organohalide with palladium 0 by way of an oxidative addition. The oxidative addition is going to generate a palladium species, which is now in the +2 oxidation state. Now, it turns out that tin is actually quite capable of undergoing transmetallation on its own, especially if we have the R group positioned well. It does really well with sp2 hybridized R groups. And so what we're going to do in this stage is sort of our metathesis reaction called transmetallation. And the palladium says, well, halide, it's nice to know you, but tin, as we saw in the radical unit, tin loves bonds to halogen, makes very stable bond. So we're going to see transmetallation where what falls out of this reaction is SnBu3 attached to X. What does that leave our palladium with? The palladium being the other metal that accepts the other thing that was attached to tin is now going to be attached to the R group. It's in its +2 oxidation state. Well, from here, we can do reductive elimination. When two carbon atoms are bonded to palladium, doing a reductive elimination process works really well because you form a very stable bond, a carbon-carbon bond. And we love to make carbon-carbon bonds. So here's our new bond in this case. As much as we love the Heck reaction because it uses so many cool types of reactions of transition metals, just taking two things and plugging them together without requiring a functional group being generated, which is a requirement of the Heck reaction, is ultimately advantageous. So, is the Stille coupling, is that superior? Sometimes, especially when you have tin around, it's amazing if you got tin around. How many times do we have tin around? A few radical reactions, but otherwise we haven't seen it too much. What was the deal with tin? Why don't we like it? Oh yeah, that's right. It's a cumulative toxin. So the thing with tin, organotin reagents, is they're super toxic. So if you don't have to have tin, like if it's just not already there, I don't want to go to the trouble to install it. Okay, let's try to evolve this idea of oxidative addition, transmetallation, reductive elimination. Oxidative addition, transmetallation, reductive elimination. Let's take that one step further and consider an alternative cross-coupling reaction like the Negishi cross-coupling reaction. So the Negishi cross-coupling reaction uses the same strategy, except we're going to use an organo-zinc species instead of an organostannate, an organo-tin species. So organo-zinc species have super low toxicity, especially compared to organotins. The organo-zinc is in the +2 oxidation state. We're once again going to rely on a palladium 0 complex to accomplish the transformation. And we're going to just couple an R group to, in this case, an arene. But this would work on any sort of sp2 hybridized organohalide, and really a lot of sp hybridized ones as well. So here's the mechanism, just to kind of emphasize the point here. For this reaction, we're going to first do oxidative addition, where the palladium climbs in between the carbon and the halogen bond. That's going to convert our palladium 0 complex into a palladium 2 complex. Okay. Now, in the presence of our organo-zinc species, we are going to do transmetallation and kick off zinc halide. So the zinc is not catalytic, just like the tin was not catalytic, but who cares about zinc? I mean, it's present in us and our proteins and that sort of thing. So it's not that big a deal. Like, it's not toxic like tin is. I mean, obviously you got to be careful when you handle organo-zincs, and I'll get to that in a second. But yeah, anyway, not a big deal. Okay, so after transmetallation has occurred, and I'll label that step here in a second, we form a palladium 2 complex, which is now adducted to 2 carbon species. Again, this step was transmetallation. We've seen this intermediate before. This intermediate readily undergoes reductive elimination to form a carbon-carbon bond. In this case, it's the arene attached to the R group. So it's the same sequence of events, but we relied on a less toxic organo-zinc reagent. So this seems to be superior, right? Well, the issue is hazard alert. Organozincs are not water stable. You know, I don't know how pyrophoric they are. They're much less, if they are pyrophoric, like an organolithium, they're much less so than the organolithiums. I feel like, but I always buy them as solutions that have to be titrated. So they're interesting, but they've got some stability issues. So hazard, I'm going to say low stability. I mean, it kind of is a bummer if like you have to exclude water to such a high degree all the time for these cross-coupling reactions. These are supposed to be easy. It's really supposed to turn organic synthesis into sort of Lego building, where you have these pieces that you just have to merge together to get the types of reactions that you want to see. Okay, enter the next one, sort of the last stage in evolution. All of these things have proven to be highly useful, and there's other variants of them, but it's hard to really undersell the importance of the Suzuki reaction, Suzuki-Miyara reaction. So the Suzuki-Miyara reaction is like the others, but it's a cross-coupling reaction where transmetallation occurs with an organoboron species. So these organoboron species they're not as non-toxic as zinc, but they're way more stable than zinc, and they're way less toxic than tin, even though they're not as stable as the tin reagents. And tin reagents aren't like rock stable, but so they're kind of middle of the road stability and toxicity. Okay, so what you can do is you can take your sp2 hybridized halide. It could be, again, either one of these. Now what you're going to do is add a boron agent, and these boron agents could vary quite a bit. This has been studied extensively. And what you do is you add palladium 0 along with some sort of base. It's not always required in some of the other cross-coupling approaches, but it's definitely required here. And our net reaction is that we're going to couple, I should make this R prime on the boron. We're going to couple the R group to the aryl halide, much like we did before, and in fact through a very similar mechanism, where we first take our sp2 hybridized carbon atom and we react that with palladium 0 by way of an oxidative addition event to give us this species. Now, along the way, the R group being attached to the B, OR prime, OR prime. This could be a number of things. This could even be fluorine atoms. If it's fluorine atoms, you can kind of get away without the base if you have enough fluorine atoms. But you typically let a base interact, and this base can be something pretty mild, nothing crazy. Like sometimes it's carbonate, where it's a pretty weak base. But we just need some kind of at least slightly nucleophilic oxygen atoms to engage with the boron atom to render the boron now negatively charged. And we've seen this in one of our mechanisms where we wanted to take a carbon-boron bond and make it more electron-rich by adducting something to the boron so it's now negatively charged. At this point, this mixture of these two species can readily undergo transmetallation, but that base really is required to get us there because boron's not that metallic. So yeah, anyway, we need this boron with a negative charge complex to do the actual transmetallation. I'll make note of that down below. But after the transmetallation, we're at the aryl attached to an R group, the palladium aryl now attached to an R group, which can undergo reductive elimination. Now, just like before, we have the things that are not catalytically active, and that is, the boron agent, just like it was for the zinc and the tin from the previous studies. So we have this. After reductive elimination, we regenerate palladium 0, and the transmetallation is going to also generate our BOR prime, OR prime base, and X. And that just sort of washes away. Okay, so we have our product. Now, the key takeaway here is that the boron, as we say, neutral boron transmetallation is slow. I mean, it's not that metallic of a metal to start with. But boron 8, and 8 being you have a negative charge in the boron, boron 8 transmetallation is fast. And so as a result, typically you add a base to make it negatively charged. You could have a trifluoroboron salt, where you've got your R group adducted to a boron with 3 fluorine atoms attached to it and a negative charge. Sometimes that's the way to go because that's more inherently reactive, especially if you have a base-sensitive species. But as a result of this reaction, there's libraries upon libraries of boron reagents that you can use in this reaction. And it really has become a mainstay in all of chemistry. And in fact, people have built robots that are just automatic Suzuki cross-couplers. And so you can just let robots start to build the chemicals you want. I think I'll throw a few papers like that in the papers to consider for your journal club presentations. But yeah, it's really a mainstay, thousands upon thousands of papers. Everybody uses this in medicinal chemistry to generate drugs quickly because it's just so reliable. It uses a catalyst, so it's a bit more green than most species. And you can just kind of stitch two things together. And like I said, it makes making molecules start to feel more like building with Legos, where you just have to clip the pieces together and you're good. Okay, so that'll do it for our transition metals section. Hope you enjoyed it. I always enjoy kind of talking about it and finishing up on this and just, seeing how even as complicated as some of these metal complexes are, they rely on the same types of reactions over and over again to accomplish some really tremendous things in organic chemistry. So anyway, That's it for now. See you next time.